Good afternoon, everyone. So I'm speaking to you from Melbourne, and today I'm going to give you a little bit of a highlight about the MCFP, the Materials Characterization and Fabrication Platform, which I'm a part of. And you can see that we have here lots of different capabilities. We're a very broad-reaching research platform within the University of Melbourne. And we sort of break up into 6 different research nodes or capability areas. And in particular, I look after our electron and ion microscopy, and the ion microscopy part will be a little bit of a focus for today. And we have strong capability also in atomic force microscopy with my colleague Tian, who is also with us today as well. And I'll highlight a little bit about our AFM as well. But then we spread out into some of the more biological imaging aspects, so optical fluorescence imaging and super resolution imaging, X-ray characterization through XRD and XRF, and also mass and flow cytometry, with mass cytometry also being one of our flagship capabilities. So we're a very broad-reaching research platform within the University of Melbourne, and we are also the University of Melbourne hub of the ANFF Victoria node as well. And we have a direct connection then down into MCN in Clayton through Dan Smith, and he looks after a majority of our nanofabrication capability on that kind of large scale. But within our ion microscopy and our AFM microscopy capabilities, we also do some nanoscale fabrication. And really that's the topic of today's talk, is to highlight the nanoscale fabrication that we do within MCFP using these capabilities. So first of all, I'm just going to highlight quickly the Cypher AFM, for which Tian looks after, and some of the capabilities that this instrument affords us. And I'm sure that many people in the audience are already very familiar with atomic force microscopy and what it can give you in terms of very high spatial and depth resolution imaging. And that precision metrology that comes from that as well. So being able to look at surface roughness and nanometric topography and getting those X, Y, and Z metrics out of your system. So of course, AFM very, very good at doing topography and surface roughness, and therefore extending it into the fabrication space, outstanding at looking at nano and micro scale patterned surfaces. But the thing that becomes very, very interesting with the atomic force microscope is what happens when you start playing around with the cantilever and the tip that you're actually using. So if you start to perhaps functionalize or add an extra component onto that tip on the end of your cantilever, you can start to probe mechanical properties of your surfaces. And in particular, you can start to look at the phase imaging from the AFM to pull out things like elasticity of your sample surface. And then if we start to go down kind of the electrical route of things as well, you can do things like magnetic force microscopy, where you can combine a topography image with a magnetic force image and then get these lovely 3-dimensional images out that show you both a combination of where your topography and your magnetic force is as well. So this is an example of a hard drive surface here, collected from the Cypher AFM. And some recent work here highlighting something else that our Cypher can do, which is conductive AFM as well. So again, taking that topographic image, that very, very high resolution topographic image, but now looking at the current that can flow through your cantilever and through your tip and overlaying that with your topography. So what we have here is a doped polysilicon film, 2.5 micron square image here, and the scale is in nanoamps. And this is showing you where there are very nanoscale domains of increased conductivity within this surface as well. So this allows you electrical characterization on the nanoscale. And then pushing this further into the fabrication space, we can actually do lithography on our AFM as well and do other things that involve making mechanical changes within the surface using that tip. So here we're talking about something called piezo response force microscopy, or PFM, and imaging and lithography using that capability. And in PFM, what we are doing is we're applying a bias to our cantilever and our tip, as we scan across the surface. So here is a map of the negative to positive bias that is applied onto the tip as it scans across a given area on a surface. And this particular surface is a single carbon nanotube PVDF polymer composite. And what we measure then is the deflection of the cantilever as a result of both the spatial and the voltage bias on that tip. And the image that you see in the middle here shows that deflection response, and the bright areas are indicating where that polymer composite is expanding or contracting more than other areas based on this particular voltage. So that's that piezo response mechanism. And from that, you can pull out lots of metrics about how much it is responding from a given voltage. And the goal here is to make flexible generators, things that will generate electricity simply by kind of wiggling and moving them around. But the lithography aspect, how you can turn that into a real fabrication thing, is to then actually create patterns on surfaces using that same method by applying a strong bias into a polymer. And so what you see here is the MCFP logo written into a PVDF film using PFM lithography. So that's a bit of a highlight of some of the more advanced methods of using our Cypher AFM within MCFP to support some of our fabrication research. But the prime topic for today is really to talk about the helium ion microscope. And this is how we're going to get into these fabrication of these plasmonic nanotweezers. So foremost, the helium ion microscope is a microscope, and you can really compare it to the scanning electron microscope. And the examples that I'm giving you here today are very broad. So we're going from materials into biological structures. But one of the key things I want to highlight here is because we're using now a helium ion beam instead of an electron beam, we can get away with doing things without conductive coatings, for example. And we typically will get better spatial, but very importantly, better surface sensitivity with this technique than you will with an SEM. So the examples I'm giving you here today are just a few of the ANFF related and fabrication related work that we are doing. So we have some cantilevers that are functionalized, work with diamond. We do lots of work looking at biological structures here. So again, a thin diamond film, and more recently, some very, very gorgeous work coming out of MCN and the Nanoscribe. So these are incredibly finely printed polymers on glass slides. And this is showing the Eiffel Tower with the features here, less than 400 nanometers in size coming out of that technique. And just a reminder, all of these are generally insulating materials, and we can get these gorgeous images without needing that extra gold coating step. But the most interesting stuff, of course, comes from using that ion beam to actually do fabrication. So using it like a focused ion beam instrument. And the examples here that I've given you are some of the more interesting things that we're doing. I'm going to be talking about these plasmonic structures in just a moment, but something I wanted to highlight here was the molecular diffraction gratings that we've fabricated in silicon nitride for a group in the University of Vienna. So very, very thin slits, 40 nanometer slits here across a large area in an insulating material such as silicon nitride. So yeah, very, very fine control over where we can place these patterns into insulating materials. And so then to wrap up some of these application overview that I'm doing here is talk about these plasmonic nanotweezers. And the group at the University of Melbourne, led by Ken Crozier, has always been looking at these, typically using what are called these double nanoholes here. So these are a double nanohole structure using gallium fib. And this is a very intuitive structure to create a plasmonic device. It's easy to understand why a human would think of this particular structure to create this very small gap here. But they allowed machine learning to take this structure, modify it a little bit, and see if it could improve the design. And indeed it did. So it came up with these much more squiggly, non-intuitive designs that they then wanted to fabricate to test out. And it turned out these are far more efficient at trapping nanoparticles. So using the gallium fib, this is what they resulted with. This is a coupling ring structure here as well. But you can see that the internal, this very, very small plasmonic device in the middle doesn't really match the design that they wanted. So they turned to the helium ion microscope and its much sharper, finer beam to take a look at what we could achieve. And this is an example of one of the plasmonic devices here. So this is the pattern to be created with a 30 nanometer gap in the middle. And this is what the helium ion microscope was able to achieve using our neon beam to do the coupling ring on the outside and the helium beam in the middle to fabricate that structure. And you can compare the design and the results side by side to see that the fidelity of that reproduction is outstanding compared to the gallium fib, for example. And if we tilt the sample on its side as well, you can see how vertical and very sharp these cuts can be with the helium ion microscope and the neon and the helium beam, because it is a very collimated, very vertical beam, giving very, very sharp cuts as well. So the design reproduction is absolutely outstanding. And as a result then, when we fabricate these devices to actually test them, so this is now a double ring coupled plasmonic device with two different algorithmically designed and one standard double nanohole device. If you look at the simulations versus the measurements here for the cathodoluminescence, you can see that they match very, very nicely. And the important part of these metrics that I want to highlight here is that down here, in these very, very low intensity regimes, we're able to get nanoparticle trapping with these plasmonic structures, whereas the more intuitive double nanoholes cannot achieve coupling at these very, very low laser powers. Okay, so to very, very quickly wrap up, that's everything I wanted to give you. And I'm very well aware that was an incredible whirlwind tour through some of our work. Too many people to acknowledge name by name, but here is everyone that we work with and everything that you've seen today. I'm very, very happy to take a question if there is time, but otherwise, please do not hesitate to get in contact with me. Visit our website here. And thank you very, very much for listening.
There's one question. Can you comment on the speed redeposition of milled material and advantage over gallium fib?
Okay, of course, redeposition is an issue. The milling speed in the helium ion beam and the neon ion beam is, of course, far less than it would be for a gallium fib. So, yes, it's a challenge to deal with redeposition. It's really down to the choice of the way in which the pattern is created. And a lot of this work is developmental in that we really need to try it out and see what works. But basically, any of the conventional understanding about how you would generate a fib structure using a gallium fib is directly applicable generally to the helium and the neon ion beam. You just need to consider that with the helium beam, the implantation depth is going to be much greater. The neon beam is going to be closer to that with the gallium fib as well, in that it's going to be much closer to the surface, but your speeds are going to be less. So you need to pick and choose the fights carefully as to whether the neon beam is the best, the gallium fib is the best, or the xenon plasma fib is the best in terms of the scale that you need to really fabricate with these devices.
Thank you.